Hello and welcome to the solutions to sheet 2 of the sets section of my Formalising Mathematics 2022 course, and it's more stuff about sets, unsurprisingly, and X is a type, so X is where everything's going to be a subset of X. So, you know, the basis of lean is type theory, not set theory, but there are some sets in in lean, but those sets are all subsets basically. So A, B, C, D, and E are subsets of X, and X, Y, and Z are elements of X. So what have we got to do here? We've got to prove that X is in univ. So this is, it's a bit weird, right? X is a type, so I always keep saying, just pretend it's a set. Types are the same as sets. But somehow set X and X are not quite the same, right? And what's going on here is there's a certain subset of X, which is the subset of X consisting of all the elements of X. And you kind of think, well, that's X, right? But it's not X because X isn't a set. So it turns out it's called univ. Univ set X is the set of all elements of X. And it's defined to be, univ is defined to be the things in X such that true. So X is in univ is by definition, this is going to be by definition true. We could really, do I want to go down this rabbit hole? Let's see if we can. Okay, right, I'm opening the box. Let's switch notation off. Set option PP notation. Listen, I say that up here, right? X is in univ is by definition equal to true. But let me just show you why that's true. Look, let's switch notation off there. And now instead of X is an element of univ, it says has mem.mem X univ. And now we could unfold it. Unfold has mem.mem. That's we gotta be more delicate. Let's just do delta. Delta is a really, oh no, it's never gonna work. Yeah, can we do donefold? Oh, bingo. Donefold has mem.mem, set.mem, and now we need to unfold univ. There we go. So you see, we've this done fold. This means definitionally unfold these. Don't do anything except unfold the definitions. And what we've done is we've unfolded all the definitions inside. In fact, what can we unfold true? Can we unfold univ first? Does it? Yeah, we've got to be really careful. We're going to solve the goal by accident. Let's done fold univ. There you see, lambda a true. It's the function that sends everything to true. So the goal is actually true. So let's put notation back on because that was a bit crazy. And you prove true with, I don't know, triv will prove true. So there we go. And you don't need to do the unfolding, of course. Triv, like many tactics, just completely sees through definitional equalities. And similarly here, X is in the empty set. That's defined to mean false. So we've got to prove false implies false. So we've got to write down a function from the false type to the false type. And why don't we use the identity function, exactid, has done that one. How are we going to prove that a random set A is a subset of univ? We could use intros X and HXA, I guess. And now we're going to prove X is in univ, and so that's just triv again. There we go. Empty set is a subset of A, I suppose so. Intros, there's two ways to do this. X, HX empty. Let's just call it HX. No, there's only one way. X, so X is in A. This X is in the empty set. That's false, right? So it's not just. Obviously X is in the empty set is a false statement, but X is in the empty set is by definition equal to false. So I could do change false at HX. So how are we going to? Well, we've got a false hypothesis, right? So there's various things that we could do with it. We could do cases on HX. That would solve it. You see, that solved it. Another thing we could do is do X. We could do the X falso tactic, and now that's changed the goal to false, and so now it's an exact HX. There. So there's various ways of doing it. So unnecessary, right? Unnecessary line. So do you know what? What about this? What about we could do rintros X and then there's no cases left. There you go. That solves it in one line. And now there's an error now, and the error is don't do any more tactics because you've finished. So there's a kind of a cool proof. Solves goal in one line because you do intros then cases. That's the cases HX proof, but there aren't any cases. And now what? A intersect empty is empty. That shouldn't be on this sheet. Okay, those aren't going to be there. I'm going to delete those. This never happened because I haven't talked about how to prove equality of sets yet. So rather prematurely, that's the end of this video. And by the time you see sheet 2, those examples won't be on it. We'll come back to these later. I'll talk about, you see, we've got to prove that two sets are equal here. So we'll do equality of sets later because you need another tactic.